Good morning, everyone. I first of all thank the organizers for giving me an opportunity to present my work in the Sriram Fest, no less, very special occasion. Everybody starts with thanking Sriram and talking about how his work has influenced their careers. Well, he was my PhD supervisor, so he set the initial conditions for the evolution of my career. So I think the influence is really obvious. And also, today I'm going to talk about non-reciprocal interactions. So we started discussing non-reciprocal interactions more than 10 years ago with collaboration with Ramin, the creator of Janus colloids. So it's like my career has stayed close to the initial conditions, let's say, and I'm happy about it, more or less. Okay, so I don't know if it's a good thing or a bad thing. It's just like, it's a thing. Okay, so I'm talking about, so the title of my talk is Effervescence in a Scalar Mixture with Non-Reciprocal Couplings. So I'm considering a kind of active matter where non-reciprocity is the only source of activity. I'll be considering conserved densities without any orientation. So they are, if you want to think about a microscopic realization, those would be isotropic particles. And I'll talk about how, if you consider a mixture, then effervescence is inevitable. And what is effervescence? It's a term that we coined to talk about a kind of spatiotemporal chaos that you can see in these systems with non-reciprocal couplings, where you see the effect of the underlying phase separation dynamics in the sense that we see a steady state where there is a spontaneous creation and annihilation of phase-separated droplets in a background of oscillating densities. Sometimes that manifests as a traveling wave, sometimes not. So that is effervescence. Okay, so, well, we all know here about non-reciprocity. So it is synonymous with action-reaction symmetry breaking, which means that if you consider two particles, then the force that one exerts on two is not equal nor opposite to the force that two exerts on one. Examples are pretty ubiquitous in active matter. So active colloids, for example, is something that that has beautiful manifestations of this non-reciprocity, starting from isotropic colloids, which can form dimers that can spontaneously move, chiral molecules that can rotate, and so on. If you add another layer of complexity and add orientation, they can spontaneously break the chiral symmetry. If you consider a collection of these colloids, they can phase separate, but also have manifestations of non-equilibrium, like in these systems where they self-propel and leave behind a collection of particles. They're also seen in this very nice externally controlled colloids of Clemens-Beckinger's group, where each of these colloids have a vision cone in which this particle here only interacts with those that are in the vision cone. Okay, so with that, let me first give you a general scheme of before I introduce to you the equations that describe the non-reciprocal Carnot-Heyden model. Let me give you a quick sketch of what it does. So we consider a mixture of particles with number conservation. Some of them, or at least one of them, can undergo phase separation driven by attractive free energy. So in the absence of non-reciprocity or any kind of activity, they phase separate into bulk phases. Now, when we include strong enough non-reciprocity in the most minimal way, the parity and time reversal symmetry of the steady state is broken, and the phase separation is arrested. The system forms bands. I mean, this is one of the steady states the system can go into it forms bands and starts moving in a spontaneous direction. And this model was introduced by two groups simultaneously. One with us, so and the other was by Cristina Marchetti's group, so you, Bhaskaran, and Marchetti. So if you want details, please look at these two papers. Okay, so if you now take a cut through the density profile when the systems are separated into bulk phases, then you see that the phase-separated domains are located at the same places, at the same spot. So there is the regions, the phase-separated domains, they collocate. Now, if you take a cut through this traveling wave, then you can see that the domains now have a finite phase difference between them, a sign of broken parity. Another way of seeing this broken parity and chasing interaction is to, in the simulation, stay at a fixed point and plot the fields phi1 and phi2 as a function of time, as you would in a phase portrait, and you see that a limit cycle emerges. And this limit cycle emerges no matter what point you look at in space. So now I show you the equations that describe the non-reciprocal Cahn-Hilliard model. So because we are looking at a mixture of particles, we can step away from detailed balance equilibrium by manipulating the chemical potentials with terms that do not carry gradients. So the chemical potentials have two parts, one which is derivable from a free energy and another which is written using these non-reciprocal interaction coefficients alpha ij. Alpha ij is a fully antisymmetric matrix, so it's no way you can derive this from an underlying free energy. In this talk, I will only consider two distinct species labeled with indices 1 and 2. And the general dynamics I will consider is when this, so that is described by just one coefficient of non-reciprocal interaction, alpha. And in this talk, I will consider the case where alpha can depend non-linearly on the fields. But first, I will talk about when the non-reciprocity is constant and show you what kind of phase behavior we get when we do that. The general properties of the steady state that the general dynamical behavior of the set of equations is independent of the free energy that we choose, but we choose it to be here to be of a rather simple polynomial form, while each of these species can phase separate even when you turn off interactions into bulk phases with compositions C1 and minus C1 or C2 and minus C2. And we also introduce a coefficient of reciprocal interaction, which is given by this parameter chi. Okay, so now in order to get an idea of the dynamics, we do what we can do the easiest, which is to look at the dynamical matrix that couples the perturbations away from a homogeneous system given by phi 1 and phi 2. And this dynamical matrix is now asymmetric. So because of this parameter alpha, so D12 is not equal to D21 precisely because of this coefficient of non-reciprocity alpha. So it can now have it can now have complex eigenvalues. So if you look at it is most instructive to look at the eigenvalues of this dynamical matrix in two different slices of the rather large interaction, rather large parameter space. The first is to look at it in the plane of reciprocal and non-reciprocal interactions, chi and alpha. And here you see that there are points in the parameter space where the two eigenvalues merge into one, and then when you crank up the non-reciprocity further, then the two unstable real eigenvalues get converted into a pair of two unstable complex eigenvalues. And that is where, and the lines where the system has two identical eigenvalues are these lines of exceptional points, and they separate the bulk phases from those where we have oscillations or traveling waves. And here I show you two phase diagrams for two different parameters with two different free energies. So one in which C1 is not equal to C2, that's this one, and for here C1 equals C2. So the overall form of the phase diagram stays the same, that for every value of chi, there are two values of alpha for which you can get, beyond which you can get oscillatory phases. Okay. And exceptional points are everywhere in active matter. One can find these in polar active matter in this paper called Non-Reciprocal Phase Transitions that has been referred to quite a few times, so I guess everyone knows about it. Okay, so here I show you. Okay. So here is a video showing how, if you start from random initial conditions and solve the equations, solve the PDEs directly using pseudospectral methods, you can see that initially there are these fluctuations, oscillations between the densities which coarsen, and then the coarsening is arrested, and there's a selection mechanism by which a wave number is selected, resulting in a traveling wave in a spontaneously chosen direction with a fixed angular frequency. Okay, so the other slice of the parameter space which is instructive to look at is the space of average composition. Remember that this is a pattern formation in a system with number conservation where the average composition can be tuned to tune the final dynamical behavior that the system shows. So here is a phase diagram in the average composition of the two species phi 1 and phi 2. And you can see that this here, you can see that the complexity in the behavior, in the dynamical behavior. For some compositions, you get a reentrant type of a bulk phase separation, and then right in the middle, you have these the traveling waves that I showed you, but right at the edge, one can go also from stable homogeneous states to a traveling lattice through a conserved version of a Hopf bifurcation. So this is a zoomed in, this is a zoomed version of the phase diagram in the middle. You can see that this edge, so in the middle are we find the traveling waves that I showed you in the previous slide, and then the edge are the traveling lattices, so I'll show you what that looks like first. So this is now a proper two-dimensional pattern. So the two patterns are incommensurate. So there is a local polarity produced due to this non-reciprocity, and with this because of this local anisotropy, now this system can show time reversal symmetry breaking and move in a spontaneous direction. Okay, so before I conclude this part with constant non-reciprocity, let me just quickly give you a summary of some features of non-reciprocal cantilevered model. So first of all, note that, as I said this before, that the activity can be introduced to second order in gradients. There is no need to go, for a single species, one has to go to higher order in gradients to write down a dynamics that cannot be derivable from a free energy. In this case, we don't have to do so. This is explicitly, NRCH describes explicitly the dynamics between two distinct species. Of course, in this seminar, in this conference so far, there have been many examples where non-reciprocity doesn't arise from interaction between different species, but for example, a coupling between polarity and position. So Janus colloids is a good example, colloids with vision cone, and then this I had completely forgotten and I got reminded by Sriram's nice talk. Where you have this, in the sedimenting lattice, you have this coupling between the local coupling and the tilt and the drift because of that. Okay, and here in these systems, it's rather simple because non-reciprocity is the only form of activity. No self-propulsion or active rotation has been put in. And hopefully I've impressed upon you so far that the pattern formation ability of the system is very rich. You can also see some other work from the group of you at Thielen, particularly this paper, which explores this in further detail and gives it a formal structure. Okay, so now I come to nonlinear non-reciprocal interactions, where the fields alpha, the interaction alpha can depend on the fields phi1 and phi2. Today, in this talk, I will focus on a particular form for alpha and a particular form for the free energy. But let me, I will just claim right now that whatever I tell you about the dynamical behavior of these equations are independent of the details of F and the details of alpha. So if you are interested, just talk to me during lunch or during tea, and I can tell you more about it. So for now, I will choose forms for F and alpha such that we can write these equations as a conserved version of the complex Landau-Ginzburg equations. So we do that by writing down a complex field, defining it in this way, and we choose the free energy and the nonlinear non-reciprocal interaction parameter alpha to be functions of the modulus only of this complex field. Okay, so with this simplification, we have this equation, which looks rather simple, but has a lot of rich dynamics, as you will see in the next slide, or 2 slides. But as soon as we do it, as soon as we write down we choose this particular form for F and alpha, we can write down an exact solution for the traveling waves, which is given by an arbitrary wave number Q, but the amplitude depends on the wave number in following this equation. And here I also show you the angular frequency as a function of the wave number. And you can see immediately that the angular frequency, the fact that there is number conservation in the system is explicit in the number frequency because you have this Q square hanging around, which if you look at the complex Landau-Ginzburg dynamics doesn't appear. What does it mean? It means that global oscillations of densities are ruled out in the system with number conservation. So the simplest possible oscillating state that you can have is this traveling wave and not really global oscillations. Okay, but now that we have a an analytical form for the traveling wave solution. We can put in perturbations around that and see what parts of the parameter space described by the alpha 0, alpha 1 parameter are.
Can you just go back on the slide? We're trying to keep up.
I'm sorry, am I going too fast?
I'm honestly taking notes.
Oops, I can send you the slides.
Okay.
But, Shyam, do you have a question? Like, that's just the trial wave solution. Okay. Given that, I realize I'm going very fast. Are there questions? If not, I'll just continue. Just ask me later, okay? Okay, so we can now allow small perturbations around the traveling wave solution, and look at the eigenvalues of the dynamical matrix that couples linear perturbations given by phi q and phi q star in wave number space about the traveling wave solution. And when we do that, we find two eigenvalues, one which describes the relaxation of a amplitude-like quantity, and another which describes the relaxation of a phase-like quantity. So the eigenvalue that describes the relaxation of the phase-like quantity is actually can become unstable at small values of wave number, and that we expand in small values of k to write like this, so that there is the phase travels with a phase velocity v that depends on the alpha 0, alpha 1, and also the wave number of the traveling wave around which we're looking at, around which we are doing the stability analysis, and we get two different, and the perturbations, they decay or grow with two different diffusion coefficients, one along the direction of the traveling wave, and which is given by dl, and the other which describes the diffusion in the perpendicular direction given by dt. Now, if you look at this, you can see that the traveling wave is unstable if either of these diffusion coefficients change sign, and there are three different ways in which the longitudinal part of the diffusion coefficient can change sign. The first is a conserved version of the Eckhausen stability, which appears in the systems where there is a pattern formation with a wave number q. So that would occur also if alpha 0, alpha 1 were both 0. There is an instability that occurs at finite wave number beyond this threshold value of the wave number of the traveling wave, which is associated, which occurs only which can happen even when alpha 0 is 0, only with alpha 1. But the most interesting one, and the one that probably which probably leads to the destruction of the traveling wave fastest, is the one which has contributions from both alpha 0 and alpha 1, and which is independent of the wavelength of the traveling wave around which we are doing the stability analysis, and that is this term. And you see that this is non-zero when this is negative when alpha 0 and alpha 1 are similar in magnitude and similar in size as well. So here I show you the colored regions are the parts. The colored regions are the part of the parameter space spanned by alpha 1 and alpha 0 and alpha 1, for which the traveling wave is unstable for a given wave number. And you can see that as we go to larger and larger wave number, there are large parts of the parameter space spanned by alpha 0, alpha 1, where this particular traveling wave, with this particular wave number is now unstable. We can also verify these relations in numerical simulations, starting with a traveling wave with a given wavelength, and see whether or not it is stable. That's shown here. Okay, now that we have an idea of which part of the alpha 0, alpha 1 plane the traveling waves are unstable, the question is, what is the final pattern that we observe when we let it run for a large enough amount of time, given that, yeah. So what we observe is what I described to be effervescence, which comes in two forms. which we call effervescent waves and effervescents. So in the first type, which we call effervescent waves, there are, if you look at the modulus of phi, you see this, that there are droplets where the magnitude of phi modulus is close to alpha 0, square root of alpha 0 by alpha 1. So if you remember, let me go back to the expression of alpha here, and you can see that this is, so at this particular value of modulus phi, the coefficient of non-reciprocal interaction is very close to 0. So there are domains in space where reciprocity is dynamically restored, leading to this imperfect PT symmetry breaking, which results in basically these spatial domains where droplets are formed by phase separation, but in the background of that, there are these oscillating densities. So you see these droplet dynamics on the background of which there is also a traveling wave. But there are also other parts of the phase diagram where there are these density oscillations in the background, but we do not see a clear enough traveling wave, which we term effervescent. So it comes in these two forms. Okay, so I'll show you the movies in the next slide. It's very clear looking at the movies that the dynamics occurs at a multitude of length scales and time scales. And that is also obvious when you look at the power spectrum, which is flat for large parts of the frequency. And then, of course, it decays as it should at larger values of omega. The structure factor is pretty much isotropic around, if you subtract out the amplitude for the traveling wave in this case, it's more or less, it goes to 0 at q equal to 0 as it should, and then they're pretty much isotropic, showing that a large number of length scales are associated in producing these patterns. Same for the effervescence states as well. So here I show you now a video where you can see these domains where there are droplets which are either occupied by one particle, or there is species. There are complex droplets where one species is encapsulated by the other, and so on. And here, this is a video for phi 1, and this is a video of the modulus field, which shows you how these droplets, basically, it shows you the droplet dynamics. This can be further the existence of these effervescent, the wave-like dynamics and the droplet-like dynamics is further quantified by looking at the probability distribution of the modulus field, where you see that it has two peaks. I will first claim, and then I will probably explain at the very end, that you see that this peak here, which is at values of phi lower than 1, properly non-dimensionalized and so on, this corresponds to the amplitude that of the traveling wave, which is constrained to be lower than 1, again, where space and time are properly scaled out. And the other one here, the other peak, it corresponds to the value of modulus of phi, for which this coefficient of nonlinear non-reciprocity vanishes. That's basically that's where the bimodality in this P of probability distribution of phi comes in. We call these phase-separated domain reciprocal granules and droplets, and that is because if you look at the probability distribution of the area of these droplets, there is a sharp peak very close to 0. So the droplets are nucleated at the smallest possible length scales in very copious amounts, and then they coarsen into these reciprocal granules coarsen into a droplet by this very familiar coalescing procedure to form a bigger droplet. And these are submerged in a sea of turbulence, probably Kuramoto-Sierpaszynski-like, because there is a close relationship with the complex analog Ginsburg dynamics. These two figures taken together, the probability distribution of phi and the area of droplet, is what we claim sort of can be measured if you want to see, is there effervescence in a system that is showing spatiotemporal chaos. Is it? As I said before, I will give you one numerical example of how this is ubiquitous behavior. So you see this with Cahn-Hilliard free energy. You see it if we see it if alpha has a different functional dependence on phi 1. Basically, if the form of alpha is such that it can go close to 0, then it does, and we get basically this kind of behavior just without any effort, really. So this is effervescence with the Cahn-Hilliard free energy. We see effervescence, we see effervescent waves, we see a flat power spectrum with the spikes that correspond to the angular frequency of the traveling wave. We also see phase separation that with very weird interfacial dynamics. That's because which we are trying to understand. We don't understand this very well yet. And we can finally produce a state diagram as a function of alpha 0, alpha 1 for the Landau-Ginzburg free energy, where we see traveling waves, effervescence, and effervescent waves. We can produce a similar phase diagram for Cahn-Hilliard free energy. Remember the topology of the phase diagram that I showed you in the reciprocal, non-reciprocal plane for the constant alpha. Nonlinearity, of course, modifies that, but you have a similar, it is reminiscent of the phase diagram for constant alpha as well. What we see is, of course, a special kind of spatiotemporal chaos. So the way to characterize that would be to calculate the spatiotemporal chaos, which we do in 1 dimensions, just for simplicity. And we see that the Lyapunov exponent crosses over from being negative to positive, exactly where it should, at the phase boundaries between phase separation and effervescence, or phase separation and effervescent waves. We can remember the 2 peaks in the probability distribution for the modulus of phi. One part I've already talked about, the traveling wave solution, where it comes from. The other, it prompts us to do a linear stability analysis around the other peak to see how does the 2 fields relax around that point. So it's like if you think of it as a local stability analysis, not really global, because the spatial domains are localized, right? So we see that the amplitude, we write down the dynamics for the amplitude-like and the phase-like variables, which are related to the symmetric and antisymmetric combinations of delta phi star. And we find that, so the inside a reciprocal granule delta rho diffuses with a stabilizing diffusion coefficient for positive combination, for positive values of this constant. The phase can also diffuse can relax in a diffusive way if this if this diffusion constant is positive. If this particular diffusion constant is positive, and these are the 2 lines that I showed you in this phase diagram. So beyond this, the claim is beyond this blue line, reciprocal droplets can be nucleated, but the phase field inside them is not stable. And beyond this line, both of them could be stable. So with that, I will end my talk saying that there are other parts of the phase diagram where the chaos disappears, and we just find these traveling waves with very stable droplets that fill up, and the density field within this droplet oscillates with time. Sometimes it's filled up with phi 1, sometimes with phi 2, and so on. And you see that, as I promised, that the probability distribution of phi in that case are very close to delta functions, showing almost stable coexistence of the wave with the droplets. And the claim is that when we have regions of when we have spatiotemporal chaos, these broaden out to accommodate all the different length scales and time scales playing together. Of course, you can change composition to actually find similar, but also still very interestingly enough different behavior. I will not talk about this at all because I'm done. Time's up. To summarize, non-reciprocity is a very interesting ingredient to create active matter. I mean, we all agree, I think, with that. The transition from bulk phase separation to the traveling wave occurs through an exceptional point, but it can also happen through a conserved version of the Hopf bifurcation. Nonlinear non-reciprocal interaction generically leads to an imperfect breaking of this PT symmetry, where there are spatial domains where reciprocity is actually restored with dynamics that looks very, very close to phase separation. And these droplets are continuously created and destroyed in a background of traveling wave or just oscillating densities, creating spatiotemporal chaos that we have dubbed effervescence. With that, I would like to thank my collaborators with which this work was done, and a bunch of other people that we are working. So Laya, Julia, Navdeep, Gennaro, with whom we are working on various aspects of non-reciprocal conjugate model and other aspects of non-reciprocity. And with that, I thank you for your attention. And questions?
So the state that you had, where you had a moving stripe pattern, moving sort of sustained traveling waves, together with the sort of noisy effervescence, is the effective long wavelength dynamics of that state? Is it like a fluctuating layered state, or is there more to it? In other words, you've got traveling waves, so it's like a kind of an active polar smectic or something, and you've also got effervescence going on in the background. So if you now coarse-grain and describe that phase pattern, is its effective long wavelength theory like a noisy polar smectic a la Chen and Toner? You've got bands that are traveling, so it's a polar smectic, and you've also got this effervescence happening. So I couldn't see if the effervescence is influencing the bands a lot, or the bands are just sort of staying rock steady and moving.
I would say that from looking again,
I think they are, right?
They are, because just because the bands are, I would not call them the same traveling wave as the one that we wrote down the solutions for, simply because they are,
just show the movie, the bottom, I guess the bottom left picture, So there are if you took a sort of a steady state structure factor of this system, then the fact that it's traveling won't come in. You'll get something, with something like bragg peaks in one dimension.
Exactly.
And there are fluctuations on it. So I'm just curious as to whether you have an idea of those fluctuations are just, to a first approximation, a simple additive noise that, or is there more to it?
These fluctuations occur at a small length scale.
But that's like any noise.
So it could be that when you go to a large enough system size, it could be possible to do what you're saying. Map it to a smectic with a noise.
With some noise, okay.
For the phase dynamics, I would think. That's, the spectrum, because it is...
Right, So, the noise is,
so flat. It could actually turn out to be, as you say, that it is like a polar smectic with
fluctuations,
kind of,
okay.
Just becomes a noise, it's possible. No, I didn't see any spiral defects. Those occur at a part of the parameter space that I'm not looking at all.
If you have a traveling wave, they should be there too.
I think they occur. So
I'm saying this from complex.
Absolutely. So I think absolutely, you're right. And so Navdeep Rana, who's a postdoc in LMP, living matter physics, he has a paper where he looks at basically here, this part of the parameter space, where he finds spiral defects, but there's a critical value of the alpha beyond which he doesn't see them at all. Is that right, Ramin? So there is so that's Ramin and Navdeep have a paper on this. So indeed there are. But those also, the spiral defects require, in order to see them numerically, you need to go to really large system sizes too. So he does that, very extensive simulations. Exactly. Yes, exactly. So he does very extensive simulations, and you can see defect dynamics, things, and so on.
I have a quick question. So most of the results you showed was for when phi1, phi2 had this rotational symmetry, and at least the effervescence, as you said, survives if you go away. But the linear stability lines, they probably don't, right? Because now the phase dynamics is not just diffusive, it'll pin to certain angles.
Yeah, that is true.
So then the question is, do you see something when you break this, when you have phi 1 and phi 2, you don't have any symmetry between them. Do you see things that you don't get when you have this reduced model?
So the thing is, qualitatively, they look very similar.
Okay.
Yeah, I don't know whether if we sort of see, yeah, I think they're qualitative, they're really very, very similar. The phase separation is different because in Kahn-Hilliard model, you can have bulk phase separation,
Yes.
whereas in this, if you look at the complex Landau-Ginzburg and just turn off all the activity parameters, what you see is kind of a microphase separation.
Yes.
So the bulk phase separation is very different. So I think it'd be super interesting to see what this nonlinear non-reciprocity does to the bulk phase separated state at zero flux in the Kahn-Hilliard model. But the ones with spatiotemporal chaos, they look very similar in the sense that if you measure all the quantities that we have measured, they have very similar qualitative features.
Can you, is there a way to show or see if on large scales you have an emergent symmetry
So
of phi 1, phi 2 rotations?
Don't know. It's a good question, but I mean, we've done some work in that, in basically trying to see, to look at in that direction, but it's difficult to, I mean, it's difficult to basically take the general model and see whether there's an emergent sort of phi 1, phi 2 symmetry. I can only say that the traveling waves, whether they're formed in the Kahn-Hilliard type model or the one with the phi 1, phi 2 symmetry, if you look at things like the correlation functions around if you put in noise and you do and you look at the correlation functions of the phase field, let's say around a traveling wave, they have very similar and very interesting properties that we have looked at. It's work under progress, so hopefully it'll be out soon. But so there could be that there's a critical point that governs all of the dynamics in the middle of right in the middle of the phase diagram. I do not know what happens when you go away from it, basically. Also, a point to note is that when you look at the composition plane, right, this phi 1, phi 2 symmetry really holds in when phi 1 average equals phi 2 average equals 0. When you go away, you basically have Kahn-Hilliard dynamics, and all of the shenanigans was to really write down the traveling wave solutions analytically to enable us to do a linear stability analysis. So, but that's really at one point, doesn't hold anywhere else.
Okay, if there's no further question, let's thank Suropriya again. And let's thank all three speakers of the session.